Welcome to the Unit 6 Integration Test Review. We'll be tackling 20 problems covering Riemann sums, definite integrals, and the fundamental theorem of calculus. Get ready to test your integration skills. Problem 1 asks us to rewrite the definite integral from 1 to 11 of sine x over x dx using sigma notation. This means expressing the integral as a limit of a Riemann sum. The general form of a Riemann sum for a definite integral is the limit as n approaches infinity of the sum from I equals 1 to n of f of a plus I times delta x times delta x. For this integral, a equals 1 and b equals 11. Delta x is b minus a over n, which is 11 minus 1 over n, or 10 over n. Putting it together, the sigma notation is the limit as n approaches infinity of the sum from I equals 1 to n of f at 1 plus I times 10 over n times delta x, which is 10 over n. Substituting the function sine x over x, the complete sigma notation is the limit as n approaches infinity of the sum from I equals 1 to n of sine of 1 plus 10i over 1 plus 10i over n times 10 over n. Problem 2 asks us to evaluate the limit of this Riemann sum as n approaches infinity. First, let's identify the components of this Riemann sum. The width of each rectangle is delta x equals 400 over n. The sample point x sub I is 100 plus 400 over n times I. The function being integrated is f of x equals x squared. Next, let's find the interval of integration. When I equals 1, x sub 1 is 100. When I equals n, x sub n approaches 500. So the interval is from 100 to 500. Therefore, this Riemann sum equals the definite integral of x squared dx from 100 to 500. To evaluate the integral, find the antiderivative. The antiderivative of x squared is x cubed over 3 plus c. So we evaluate x cubed over 3 from 100 to 500. Computing the values, 500 cubed is 125 million. Divided by 3 is approximately 41,666,666.6 repeating. 100 cubed is 1 million. Divided by 3 is approximately 333,333.3 repeating. Subtracting gives us 41,333,333.3 repeating. Problem 3 considers the integral from 0 to 4 of 2 to the power of negative x dx and asks us to order the left, right, and midpoint Riemann sum approximations without actually calculating them. Since f of x equals 2 to the power of negative x is a decreasing function, the left Riemann sum will overestimate the integral, while the right Riemann sum will underestimate it. The midpoint Riemann sum will lie somewhere between these two values. Therefore, without any calculation, we can order them as right less than midpoint less than left. Now let's calculate the left, right, and midpoint Riemann sums for the integral from 0 to 4 of 2 to the power of negative x dx using 4 equal subintervals. Delta x equals 4 minus 0 divided by 4, which is 1. The subintervals are 0, 1, 1, 2, 2, 3, and 3, 4. For the left sum, we use the left endpoints of each subinterval. L equals 1 times 2 to the 0 plus 2 to the negative 1 plus 2 to the negative 2 plus 2 to the negative 3. Calculating the function values gives 1 plus 0.5 plus 0.25, 0.125, which equals 1.875. For the right sum, we use the right endpoints. R equals 1 times 2 to the negative 1 plus 2 to the negative 2 plus 2 to the negative 3 plus 2 to the negative 4. Calculating gives 0.5 plus 0.25 plus 0.125 plus 0.0625, which equals 0.9375. For the midpoint sum, we use the midpoints of each subinterval. M equals 1 times 2 to the negative 0.5 plus 2 to the negative 1.5 plus 2 to the negative 2.5 plus 2 to the negative 3.5. Calculating the function values at the midpoints gives approximately 0.707 plus 0.353 plus 0.177 plus 0.089, which equals about 1.326. Problem 4 shows a graph of a hot air balloon's vertical velocity over time and asks whether the balloon ever drops below its starting height. Here is the velocity time graph. The balloon starts moving upward, then descends between 3.4 and 5.95 seconds before leveling off. Area A represents the ascent period, where the balloon is moving upward. Area B shows the descent period, where velocity is negative. Displacement equals the integral of velocity with respect to time. Positive velocity means upward movement, Negative means downward. The net displacement from time 0 to 7 is the total area under the curve. Since area A is larger than area B, the net displacement is positive. Because the net displacement is positive, the balloon ends up higher than it started. It never drops below its initial height. The answer is no. Problem 5a asks us to evaluate the definite integral from 0 to 2 pi of cos squared x times sine x dx. We can use u substitution, let u equal cos x, then d equals negative sine x dx. Now transform the limits. When x equals 0, u equals cos of 0, which is 1. When x equals 2 pi, u equals cos of 2 pi, which is also 1. Substituting into the integral gives us the integral from 1 to 1 of u squared times negative du. The integral becomes negative integral from 1 to 1 of u squared du, which equals 0, because the limits of integration are the same. Problem 5b requires evaluating the definite integral from 0 to 2 pi of the absolute value of cosine squared x times sine x dx. Since the integrand changes sign within this interval, we need to split the integral at x equals pi, where the sign change occurs. We split this into two integrals, the integral from 0 to pi of cosine squared x sine x dx minus the integral from pi to 2 pi of cosine squared x sine x dx. Using the substitution u equals cosine x, the first integral evaluates to 2 over 3. By symmetry, the second integral evaluates to negative 2 over 3. The total integral is 2 over 3 plus negative 2 over 3, which equals 4 over 3. Therefore, the definite integral evaluates to 4 over 3. Problem 5c asks for the integral from 0 to 50 pi of the absolute value of cosine squared x times sine x dx. We know from part b that the integral from 0 to 2 pi of the same function equals 4 over 3. The function has a period of 2 pi. Since 50 pi equals 25 times 2 pi, we integrate over 25 complete periods. Therefore, the integral equals 25 times 4 over 3, which is 100 over 3. Problem 6 asks us to identify which of the given integrals are equivalent to the definite integral from 1 to e of ln x over x dx. Let's test option A, the integral from 0 to 1 of u du. To check if this is equivalent, we need to perform u substitution. First, let u equal ln x, then d equals 1 over x dx. Substituting gives us u over x times 1 over x dx, which is u over x squared dx. When x equals 1, u equals 0. When x equals e, u equals 1. So the integral becomes from 0 to 1 of u du, which matches option A. Option A is equivalent. Now let's check option B, the integral from 1 to e of u over x du. Using the same substitution, u equals ln x, du equals 1 over x dx. The original integral becomes the integral from 1 to e of u times 1 over x dx. When x is 1, u is 0. When x is e, u is 1. This gives us the integral from 0 to 1 of u du. But option B has limits from 1 to e and du instead of dx. Option B is not equivalent. Finally, let's check option C, the integral from 0 to 1 of u squared du. Using u equals ln x, d equals 1 over x dx. Substituting gives us the integral from 1 to e of u over x dx. Limits change to u from 0 to 1. This gives u du, not u squared du. Option C is not equivalent. Only option A is equivalent to the original integral after proper u substitution and limit changes. Problem 7 involves evaluating the limit as x approaches 0 of the integral from 0 to x of e to the t squared dt, divided by the integral from 0 to x of cosine of t squared over 2 dt. This is a 0 over 0 indeterminate form, so we can apply L'Hopital's rule. Using L'Hopital's rule, we differentiate the numerator and denominator. By the fundamental theorem of calculus, the derivative of the numerator is e to the x squared, and the derivative of the denominator is cosine of x squared over 2. Now we evaluate the limit as x approaches 0 of e to the x squared over cosine of x squared over 2. Substituting x equals 0 gives e to the 0 over cosine of 0, which equals 1 over 1, or 1. We define fx as the integral from 0 to 2x of t times e to the t squared plus cosine of pi times t dt. We need to find the tangent line at x equals 1. First, find f1 by evaluating the integral from 0 to 2. The antiderivative is 1/2 e to the t squared plus 1 over pi times sine of pi t. Evaluating from 0 to 2 gives f1 equals 1/2 times e to the 4th minus 1/2, or 1/2 times e to the 4th minus 1. Next, find f prime of x using the fundamental theorem of calculus. f prime of x equals 2 times the derivative of the upper limit times the integrand evaluated at 2x. Now evaluate f prime at x equals 1. Plugging in 1 gives 2 times 2 times e to the fourth plus cosine of 2 pi, which simplifies to 2 times 2 e to the fourth plus 1, or 4 e to the fourth plus 2. Finally, use the point-slope form for the tangent line. The point is 1, f of 1, and the slope is f prime of 1. Problem 10 involves evaluating integrals with a piecewise function. The function f of x is defined as minus 2 for x less than or equal to 0 and 1 for x greater than 0. We need to find g at 0 and 3, where gx is the definite integral from minus 2 to x of ft dt. To find g of 0, evaluate the integral from minus 2 to 0. Since x is 0, which is less than or equal to 0, f of t equals minus 2 throughout this interval. So the integral becomes the integral from minus 2 to 0 of minus 2 dt. Evaluating this, we get negative 2 times the length of the interval from minus 2 to 0, which is 2. So minus 2 times 2 equals negative 4. For g of 3, the integral goes from minus 2 to 3. Since ft is piecewise, we split it at x equals 0. From minus 2 to 0, ft is minus 2, and from 0 to 3, ft is 1. The first part is the same as g of 0, which is negative 4. The second part is the integral from 0 to 3 of 1 dt, which equals 3. Adding them together gives negative 4 plus 3 equals negative 1. So g0 is 4 and g of 3 is negative 1. Problem 11 analyzes g of x equals the integral from 0 to x of f of t dt, where f is the given function graph. By the fundamental theorem of calculus, the derivative g prime of x equals f of x. Critical points occur where g prime of x equals 0, which means where f of x equals 0. Analyze the sign of g prime of x to find local extrema. Where g is increasing, look for local minima. Where g is decreasing, look for local maxima. For absolute extrema, evaluate g of x at the endpoints and critical points. The areas A, B, and C represent the signed areas under f from 0 to x, which determine the values of g. Problem 12 asks to find the value of k such that the definite integral from 0 to 2 of x cubed plus k dx equals 10. First, evaluate the definite integral. The antiderivative of x cubed plus k is x to the fourth over 4 plus kx. Apply the limits from 0 to 2. This gives 4 plus 2k. Set the result equal to 10. Solve the equation for k, subtract 4 from both sides, giving 2k equals 6. Divide by 2, so k equals 3. Problem 13 uses properties of definite integrals. Given formed from minus 2 to 2, gx dx equals 8, and quetched from 0 to 2, g of x dx equals 3. For part A, find stets from minus 2 to 0 g of x dx using the additivity property, which states state from A to C equals states from A to B plus stegs from B to C. For part B, find torques from 2 to minus 2 g of x dx using the reversal of limits property, which states from A to B equals negative breaks from B to A. For part C, find torques from 0 to 2 5gx dx using the constant multiple property, which states kf of x d equals k times f of x dx. For part D, find torques from minus 2 to 2 2gx dx using the constant multiple property. Problem 14 requires evaluating the integral from 0 to 1/2 of dx over the square root of 1 minus x squared. Without a calculator, recognize this as the derivative of arc sine x. The antiderivative is arc sine x, so evaluate from 0 to 1/2. This equals pi over 6. With a calculator, pi over 6 is approximately 0.5236. Problem 15 states that f of x is the antiderivative of x cubed over x plus sine x, and f of 1 equals 2. We need to find f of 3. Using the fundamental theorem of calculus, f of 3 equals f of 1 plus the definite integral from 1 to 3 of x cubed over x plus sine x dx. We use a calculator to evaluate the definite integral, which gives approximately 8.235. Substituting the values, f of 3 is approximately 2 plus 8.235, which equals 10.235. Problem 16 asks us to approximate the definite integral from 0 to 26 of f of x dx using the midpoint rule. We're given a table of f of x values at various x points. The midpoint rule approximates the integral by summing the function values at the midpoints of equal width subintervals. The formula is b minus a over n times the sum of f evaluated at each midpoint mi. We divide the interval from 0 to 26 into 13 equal subintervals of width 2. Each midpoint mi is the average of the endpoints of each subinterval. For the calculation, we have 13 subintervals with width 2. We evaluate f at each midpoint and sum those values. Then multiply by the width to get the approximation. Given that the integral from -3 to 3 of e to the power of -4x squared equals n, we need to find the integral from 0 to -3 of the same function in terms of n. The function e to the power of -4x squared is an even function. For even functions, the integral from -a to a equals twice the integral from 0 to a. Applying this property to our integral, we can write that the integral from -3 to 3 equals twice the integral from 0 to 3, and this equals n. Solving for the integral from 0 to 3, we get n divided by 2. To find the integral from 0 to -3, we use the property that the integral from a to b equals negative the integral from b to a. So this equals negative the integral from 3 to 0, which equals -n over 2. Problem 18 requires evaluating the definite integral from -5 to 3 of sine x over x cubed plus x squared plus 4 dx. This integral has no elementary antiderivative, meaning it cannot be expressed using basic functions like polynomials, exponentials, or trigonometric functions. Therefore, we must use numerical methods for approximation. The integral lacks an elementary antiderivative, so analytical integration is not possible. Numerical integration techniques, such as those built into graphing calculators, are required to approximate the value. Enter the integral into a calculator with numerical integration capabilities to obtain the approximation. The numerical evaluation yields approximately -0.245. Find the derivative of the integral from sine x to 5 cosine x of secant x over the square root of t squared plus 1 with respect to t. To differentiate this integral with variable limits, we use Leibniz rule. The formula is the derivative equals f at the upper limit times the derivative of the upper limit minus f at the lower limit times the derivative of the lower limit plus the integral of the partial derivative of f with respect to x. First, identify the components. The lower limit a of x is sine x, the upper limit b of x is 5 cosine x, and the integrand f of t comma x is secant x over the square root of t squared plus 1. Now compute the boundary terms. The upper boundary term is f at b of x times b prime of x, which is secant x over square root of 25 cosine squared x plus 1 times 5 times negative sine x. The lower boundary term is minus f at a of x times a prime of x, which is minus secant x over square root of sine squared x plus 1 times cosine x. Since secant x is a function of x, not t, we need the partial derivative of f with respect to x, which is tangent x over square root of t squared plus 1. This gives us an additional integral term in the derivative. Putting it all together, the derivative is the upper boundary term minus the lower boundary term plus the integral of the partial derivative. This results in a complex expression involving trigonometric functions and an integral that cannot be evaluated in elementary terms. Problem 20 asks us to find displacement and total distance given the acceleration function a of t equals 3t plus 3, with initial velocity v of 0 equals -4 over the interval from 0 to 3. First, we find the velocity function v of t by integrating the acceleration function a of t. Integrating 3t plus 3 gives us 3 over 2t squared plus 3t plus c. Next, we apply the initial condition v of 0 equals -4. Plugging in t equals 0 gives -4 equals c. So the velocity function is v equals 3 over 2t squared plus 3t minus 4. Displacement is the integral of velocity from 0 to 3. Integrating 3 over 2t squared plus 3t minus 4 gives us displacement equals 15 units. To find total distance, we first solve v of t equals 0. Using the quadratic formula, we find t approximately equals 0.915 in the interval. Velocity is negative from 0 to 0.915 and positive from 0.915 to 3. Total distance is the integral of the absolute value of velocity. Since velocity is negative from 0 to 0.915 and positive from 0.915 to 3, total distance equals 15 units, the same as displacement in this case. In summary, both displacement and total distance are 15 units for this problem.